The floor is yours.
Thank you very much, first, for the invitation. Actually, this is one of a series of work, and particularly stimulated by this workshop. When Odd invited me, we were still at the stage, okay, let's need to work on another continuous the project. And then, but the date is set for the workshop. Okay, let's hurry up. Let's present something new instead of repeating what we already presented again and again. So this is at the very early stage of this part of work. Any comments are more than welcome. So, well, we talk a lot about renewable energy and so on, but there is a price to pay about the renewable energy. That is the demanding of mineral. So the International Energy Agency 2021, I didn't update the last one, 2021 May, the report stated that a typical electric car requires 6 times the mineral input of a conventional car. And an onshore wind plant requires 9 times more mineral resource than a gas-powered plant with the same capacity. And to reach to the Paris Agreement target, that is a 1.5 degree, and in the next 2 decades, the rise of the demand of the mineral will increase substantially. For example, over 40% of copper and rare earth element, 60 to 70% of nickel and cobalt, and almost 90% of lithium. And of course, I mean, we know EMS is trying to produce the promises 2028 to supply the lithium to apply, but still, that will not fundamentally changing the situation. Those minerals, the distribution or the reserve are not evenly distributed around among the world. Some countries consider them as critical. The fundamental idea of the critical mineral, for example, defined by the US defined those minerals as they are essential to the economy and the state security, but the supply chain is vulnerable to disruptions. For example, COVID or the war and so on. And EU, the last update of the US lists about 50 critical minerals. EU has similar kind of definition, but the list changing from time to time. The first list published in 2011, there were 14 critical minerals, but the last update, 2020, lists 30 of them. And we only focus a few examples related to the energy transition. For example, the International Renewable Energy Agency's report stated that nearly 90% purification and permanent magnet production, which related to the rare earth element, come from China. And the US, in 2020, even now, during the past few years, not much has been changed. 80% of its refined rare earth element come from China. And titanium, which is actually is one of the rare earth elements, is not exactly related to the transition to renewable energy, in the US doesn't exist from 2020. And China and Russia rather occupy world about 2/3 of the world supply. EU is not any better. 98% of its rare earth element come from China, and 78% lithium come from Chile. And not mention the other examples. The point is, if the dependency on some import is not the main problem, the problem is those critical minerals was dominated by a few countries. For example, the lithium. Australia supplied about half of the world total supply, and more than 40% come from Chile, only the little part from the other part of the world. And cobalt is even worse. So far, more than 70% come from a Democratic Republic of Congo. And even world reserve, nearly half of the world reserve located there. And they were used combining with lithium for the lithium batteries, storage for batteries, and so on. So they are those essential ones. Similar situation for rare earth element. Most of them or produced by China, purification, and so on, the technology is much more advanced in China than the other part of the world. For example, even in the US, the mountain pass produce some rare earth element, but they ship to China to purify and processing they and then ship it back. Because the technology China is about 10 years more advanced than the US processing. So if just the production itself is not evenly distributed, it's not the main problem because sooner or later we could use the other. But the problem is the reserve is also not evenly distributed. So I don't know. Yes, we can see. No, this, sorry. Good. No. 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 Yeah. Yeah. Sorry. Just go back. Here. Yes. So here is a production. As we can see, the rare earth element is highly concentrated. The cobalt is even worse. Lithium is a little bit better. At least there are two countries. But the world reserve, except nickel, the rare earth is still kind of concentrated. Cobalt and lithium are highly concentrated by a few suppliers. So that is some kind of constraint of some country or EU depending on the other countries. The transition to cleaner technology had some constraint. And so because of the constraint, there is call for recycling. We know some of the minerals, for copper or orange and even some platinum groups are frequently recycled. But lithium in the world, EU and the US, is less than 1% recycling. And even worldwide, less than 5%. Yeah. Yeah, at the world level. Yeah. Yeah.
So it means that the supply chain is completely controlled by,
yes.
And those are the same firms?
Not exactly the same firm, but a few big firms. The lead acid batteries is about 99% recycled. So, but the lithium ones is not yet ready. Though the technology is almost ready. And in the sense, almost some firms already starting to do the recycling. And we have the estimation that the 2040, worldwide, about 58% the electric cars sold will be the electric ones, and which means even we don't depend on the material, but there is a lot of waste. So somehow something needs to be done. So far, the word recycling of lithium, as I said, the technology is nearly ready. 90% of the announced or already built recycling of lithium battery is located in Europe, EU, and East Asia. And 2/3 of them located in China. We know China is one of the biggest producers of the lithium battery, and the recycling, they also make a lot of effort there. And the other part of the world is still working on it. Here, yes. Of course, one thing about the recycling is, so far we don't have much data about how much energy or resource it can save, but for the other part that's related to all the other project, that is the impact of this renewable energy on the environmental issues. So at least we know the data said the steel and aluminum industry, the recycling lead to 60 to 75% energy saving compared to the primary mining. So recycling could be, even for the lithium batteries, it could be good for the society as a whole. But of course, the dependency is still there, even we use recycling, but recycling needs to depend on the original resource. So we are trying also looking for substitution. That is one of the existing one that is sodium battery. It is almost everywhere. We don't need to depend on anyone else. It's cheaper and reducing the dependency of the others. Well, so far the problem is it is with the same capacity compared to the lithium battery, the sodium ones are much bigger and heavier. But of course, if we use it for storage, it could be useful. So that would be one of the options. And so far, actually, indeed, there were a lot of development of the substitution. And again, China is leading in this part as well. And there were announced 36 Chinese companies either already starting to produce sodium battery or announced to do so, including world's biggest lithium battery producers. Okay? I'm not pretending I understood the technique behind. I don't want to embarrass myself, but here I list a group of EU countries. There are a lot of projects from EU. For example, the first two are the projects supported by the EU Zone 2020 something, and there's also the German research fundings, and so on. So there are projects try to develop sodium batteries, and the most exciting one is Timart, located in Amiens, is already trying to produce the sodium battery. So far, they only have about 10, 15 people working there, but the plan was to hire up to 1,000 people working there and produce sodium battery. And Actress in Sweden is doing similar work. That is, in China is leading, and EU is also working on it. Also in the US, at least there are some. One still working on the sodium, but EOS Energy is working on zinc battery. So the substitution is also at working. Now the question is, facing this kind of situation, what is the optimum strategy for the exporting country, initially export lithium, how they should react? And of course, what are, as we said, EU at the same time doing substitution and recycling, at which kind of rate we should do, and at which moment the recycling and the substitution should enter the market. So that is the question we would like to answer in this research. And let's have a first look about what's already been done about the recycling, the early work. Since the beginning, about the aluminum recycling literature, when the starting start is already one dominant firm and then a group of competitive fringe. Okay? And very often consider the central planners issue, which obviously is not our case. We have country and country, there are conflicts even. And so that kind of model doesn't exactly work for us. The phosphorus market is closer to our situation, which there is kind of minimum demand because the fertilizer is needed for the food supply. But different is that technology is ready, developed economy actually is doing recycling. It's the developing one they did not do because it's cheaper to import than doing recycling. So that doesn't work for our situation either. And there are some recent studies about the lithium battery recycling in the US, but they ignore about the competition, where the US doesn't yet setting up any recycling facility.
Benteng, yeah. I have a question or maybe a suggestion for extension. In particular, I think regarding phosphorus, you also have an issue of joint product.
Yes.
because, for instance, for phosphorus, if I'm correct, there is uranium coming with it.
Yes.
And this can be also part of the strategy. I mean, when you have to decide, there is not only recycling, substitution, but there is also, I mean, byproducts, right?
Yes, you're right, yes. So the recycling literature has some distance to the situation we are facing. And actually, the back of substitution has much more studies. Starting from the early Dasgupta and Stiglitz in the 80s, they have a series of work related to the backstop substitution. However, very often, they consider constant marginal production in the extraction and in the substitution. So they facing the and they consider open loop Stackelberg game. This open loop thing doesn't work for the current situation. Nobody is going to promise that they are going to supply the market. And secondly, the constant cost makes the result looks like we first using the virgin resource until the marginal cost increase to the substitution level, then we switch to the substitution. So there is no in-between, actually. And later on, people released this kind of assumption, while the substitution is not, the marginal cost of substitution is not exactly constant. These two may coexist, but still the work is based on central planners issue and forgot about the competition. And what we are facing is indeed the competition between different countries. And the most importantly, we didn't find much or almost no study simultaneously consider substitution and recycling. So that is new. Secondly, we had to take into account we are considered critical, not only essential, in the sense of Solow and Stiglitz. That is essential, meaning, well, you just have a little, that's enough. But critical is complete the transition, you need a minimum demand. So that makes a difference. We simplify a toying model. We just consider two countries. Country I is the importer, and country J is the exporter of the critical mineral. Before the recycling, the player I import from the country J, player J, and at the same time invest in R&D, try to develop the technology of recycling or substitution. Here, we ignore the situation that the country J also does the R&D. The case is, for example, China. That is for later, as I said, a series of work for the next work. Then it could change the situation. Capital TL is the moment when we start to use the new technology, recycling or substitution. And we assume that the R&D, we don't model the R&D part. We just assume we need to invest. Some kind of investment is needed in order we have the technology. So our question is, if the technology is ready, when to use it? So some notations. Smaller IXT is a depletion of non-renewable critical mineral at time t. Capital S0 is the initial reserve. ST is the reserve at time t. And the supply, of course, is changing over time, decreasing with what is already exploited to the market. Capital XT is already accumulated, supplied to the market, which means only player I will use it. The capital XT became the recyclable resource for player I. So that is a problem for player J. The resource-rich country transfer the resource from themselves to the others. And when T larger than capital TR, recycling technology is starting to supply. So the YT is the recycling at time t and with a cost. And when smaller t is larger than TS, and the substitution is starting to supply to the market. But we are not sure TR and TS, the capital one, which one comes first, which one comes later. If the substitution is ready to supply to the market, we're changing the problem from critical, the mineral from critical, maximum became essential, or could be completely out of the market. Or it's just being essential but not critical anymore. So there is a story changing there. We don't need to rely on the others. We could rely on ourselves. Then there is no more critical mineral. So they were out of the list. So the objective for country J is just to get profit from the resource. So is price multiplied by supply minus the extraction cost. And before the recycling start, the only supplier is country J, so it's just the supply is just X. But if the recycling starting to supply to the market, it has impact on the market price. Okay, there is basic requirement that is before recycling is ready, country J should guarantee that there is a minimum demand to be satisfied. If that failed, this minimum demand failed, that forcing the other country to invest more such that either substitution or the recycling technology should be coming to the market earlier than before. And then the monopoly supplier will lose its advantage. So it should not give too much pressure here. Yes?
Excuse me. So your minimal demand is not increasing over time?
It could.
It could.
All the calculation, I will come back to this point, all the calculation works if it's increasing or decreasing over time.
Okay.
Yeah, it could be. Yes?
You assume that the recycling gives perfect substitutes as
Yes.
well, right?
Yeah.
Whereas, I mean, in reality, there is a...
There could be how, not exactly the same. Here we assume the perfect
and then
substitute.
there is a friction.
Yeah, but that shouldn't change completely the story.
Yeah, maybe it's just delta that should
Yeah.
imply perfect substitution.
Yeah. Here we assume the perfect substitution. Yeah. And player J, the control, of course, is maximize the use. That is U function, X, Y, Z is a perfect substitution minus the payment and the cost of recycling and the substitution, of course, depending on if they were in the market or not, and need to minus the cost on investment. And particularly the mathematically difficult part is here before the substitution is ready, and if the recycling is ready, it's up to the importing country to guarantee you supply your recycling enough to guarantee the market demand. Okay, then that is no longer the concern of the exporting country. So I think in the Mathematics Institute, so I put more mathematical formula here. And we denote M as actually we have 4 modes. The n, small n, is the mode neither recycling nor substitution is ready. And the mode R is the recycling is starting to supply, but not the substitution. Obviously, smaller s is substitution is ready to supply to the market, but not the recycling. And mode B is both recycling and substitution exist in the market. Okay? And Vi and Vjm are the value function in mode M for player I and J. And when the stock, that is capital X, is how much critical mineral already in the market as a state. And we use the utility function UN, UR, US as just to make it easier for the utility function. N obviously is a moment, nothing else, only X supply to the market. If R, the recycling is already there, S is the substitution is there, both there, Y and Z, both there. And
you are able to model The transition from one mode to the other?
That is what we are trying to do.
Okay.
That is exactly the question we try to do, yes. So in mode n, it is easy, the question, we can easily write down the HGB equation. Okay, and IXR, that is in mode n, that is nothing else is there, and we have the first order condition also need to take into account, it need to guarantee it is no smaller than the minimum requirement. And similarly, in mode R, the only difference is Y should enter the consideration. And IX in mode R, IX is no longer has a constraint, but Y should have the upper bound, a lower bound that is need to guarantee to the market demand, but at the same time, you cannot recycling what's already in the market. So there is upper bound constraint. And not all of them can be recycled. There's always some loss. So that is even consider repeated recycling. There is always upper bound depending on how much is recyclable. And we could do the same thing for mode S and mode B. After some calculation, actually X, the optimum choice in any mode is only depending on the state, X, and the marginal value of the exporting country. Okay? Y and Z actually depending on the same. And so in the end, the optimum choice, sometimes we cannot explicitly present it, but we can prove they're only depending on the state and the marginal value function. And the HGB equation can be simplified this way. And if the, we could more complicate the model such that the perfect substitution enters the price, has impact on the critical minerals price. For example, if it's perfect substitution, the utility function is not separable. And here is also depending on player I's marginal value. But still, theoretically, it doesn't change fundamentally result. Important thing is the terminal condition. So when all the initial reserve is in the market, of course, the initial reserve could change over time. As long as it is finite, theoretically result will not be changed. Of course, the numerical result will be changed. And for the player J, that is originally nothing to supply to the market because all supplied there, so the value is 0. And for player I, in different mode, different situation happen. If in the end, all the supply is already in the market, but we don't have the recycling technology, neither substitution. So it's simply value also 0. But in the case recycling is there, then has nothing to do with X, it's just the Y, optimize the Y, how to supply to the market. But if there is a substitution is there, similar situation. And if both is there, no big deal. So that is how all the cases could be together. Now, the important question is when we should switch, if from the beginning or never happened. That is actually we consider as impulse control. That moment, that just one moment you switch, then it's done. So that is the condition for the impulse control is if from N, that is nothing there to to the recycling, that is the value function at that moment, XR, at that moment should be before the switching and after the switching. The after switching is minus the cost. And it's the same for ICE. And of course, it also could be, we already had recycling, then we introduce the substitution. Okay, that is from the before the substitution entered, the recycling is already there, the value function, and later on the value function became subscript B. Both of them exist, and the cost is a substitution. The last case actually, from what we understood, is redundant, but we put it there. That is, the substitution is already there. We try to introduce the recycling. Is it still needed or not? But mathematically, it doesn't change much, so we keep it there. And for the country J, the exporter, actually nothing happened. You are the one making the choice, has nothing, we cannot do anything. Player J has no, so the value function for player J is just continuous at that moment. Otherwise, it will changing the strategy before such that this switching cannot happen. Because he is the one, the state variable is x that could be controlled by player J.
So you impose the date?
Yes.
So in some way, is it the same as imposing the state?
It is equivalent. Actually, it's easier to get the state and then from the state back to the date. Yeah. Okay, so that is the main result, theoretically. So the condition is from the Berman equation, if we can solve the marginal value, that is pi for player I, and the marginal value for player J, just if from the value function we can uniquely solve the marginal value of the two players, then the moment we could get the state ixk is the moment such that the switching happened. Given xk depending on the supply to the market, optimum supply, we could calculate. And then the integral is xk, we get the moment t, the switching. And the condition here is the left-hand side, recall, this is the impulse control condition is the value function before the switching. Okay? And this, the right-hand side is the Hamiltonian after the switching. And nothing changing for here is the same for the player J before the switching, after the switching. And then given for player J, there is no change in the value function, but for player I, it does changing. And theoretically, we can only go so far. So we precise the functional form in order to precisely give the time. So the utility function, x and y is perfect substitute. They separatedly, but if we put it inside here, non-separatable, it does not fundamentally changing the mathematics. It makes it a little bit more complicated, but not fundamentally changing the math. Okay? And 1 over alpha is the elasticity of demand. And of course, here is just the cases of different cases. Yes. The inverse, you want the previous one? Yes. Here we have the inverse demand function, which gives us the price in the case without recycling. In the case of after recycling, we also just repeat the minimum requirement. The recycling cost, we take an easy one, linear one. The extraction cost actually is the main problem here. The extraction cost has, in the literature, there is no fixed extraction cost, how it should look like. There are different kind of literature. And here, actually, this recycling cost does not appear explicitly in the literature. However, it satisfied all our requirements that the marginal cost, depending on the stock, that is a degradation effect, and it is convex cost. So actually, this function was given to me by Francesco and Kathleen last workshop. So I use it, and it doesn't bother any of the later calculation. So it's better than the one exists, actually. So we could calculate, given the time, I think I will delete my mathematics. We could calculate the value function, the optimum demand, which is only depending on the marginal value function of player I and player J. And for all those some manipulating of the HGB equation, we could actually get explicit solution. Given the time constraint in different mode, all the modes we can calculate explicitly. Explicitly meaning could be nonlinear. We could not get the explicit solution, but it doesn't depend on the other unknown. And then the time could be here. This one, the C is actually the X, the optimum choice, depending on the marginal, and xi is given. The vi, this part is also explicitly calculated. And these two equations actually is just one, will give us the time when xi is ready. And we run some simulation. That is only one nonlinear equation system which is not clear. Otherwise, it is very clear. Here, we first look at the right-hand side one. Here is the optimum supply. The horizontal line is the stock. And here, as we said, at the very early stage, we did not yet calibrate the model. So we just randomly picking up some parameter and let the program run. And so here is the result. So don't put it too seriously about the simulation result. Mathematical results are proved, but the simulation, we didn't calibrate the model. So just to give you some idea, here is optimum supply is strictly decreasing with the state. But here is a minimum requirement. So it's decreased until it's a minimum requirement. If the minimum requirement is increasing over time, actually at this moment, decreasing optimum choice is increasing. Okay? If the minimum requirement is increasing, then it goes up until the mode change happened. And there is a huge drop of supply. Okay, given the substitution is ready, so we don't need that much, and that leads to the mode change. Given xi actually is the moment the substitution getting in, that gives us the time ts, the moment when the substitution should be there, and we also could calculate the moment when the minimum supply started. And similar situation for the value function. Well, here then the vertical horizontal line is the original reserve, and the value function of the player J, there's a fast drop, and the value function for player I. Actually, here is tangent to each other. Not only the value function is continuous, actually the shadow value also continuous.
What are happening for the shadow values at the time of the mode change?
They were for player I, the one who makes the decision, they were continuous. Yeah, but not for player J because he cannot do much. Yeah. And from the mode N to R2 recycling, looks the calculation exactly the same, but actually much more complicated. Recycling, previously, a previous work we proved that actually recycling, we may have multiple equilibrium. Here, similar situation happened because the recycling has a two boundary constraint. One is need to satisfy the minimum demand, otherwise, other part, you cannot recycling too much. So there are three possibilities lead to actually three different kind of strategy, and the result also different. And we still didn't know which one we should pick it up, actually. We're still struggling about this part. And anyhow, we do the same calculation as to the substitution, just picking up the intermediate one, that is the recycling taking the optimum choice instead of the two boundary cases. And the result is like this. It's very much similar to the previous one. The mode very much similar. But our parameter setting, as we said before, we didn't calibrate. Actually, substitution comes earlier. Of course, we didn't consider the case if we first have the recycling. Substitution will come or not. That part we didn't yet do. Later on, we will do it after the calibration. And here, actually, substitution comes earlier with the current setting of parameter. And the minimum demand, actually, in this part, under recycling, minimum supply period is longer than the previous substitution one. So it does have impact to the exporting country. And value function mode are also kind of similar to the previous case. And of course, one of the question about minimum demand, we consider actually initially we do have, actually we consider minimum demand this way. M could be larger than 0 or smaller than 0. So increase or decrease, both possible, doesn't affect the theoretical result. It does affect the simulation result. And the initial result, again, doesn't changing the theoretical result. Of course, if we run simulation, the initial result changing, then it changing the simulation result. We didn't impose any boundary condition, the terminal condition, because all these recycling, substitution, and critical, even the transition to renewable energy is just at the beginning. So if we already impose a terminal condition, it's too early. So we don't want to do that. Thank you very much.